So say, for instance, we want to look at the following points. So I have some code. I have this wrapper code, which computes the inputs for the Z2 mixed bootstrap, what I call icing mixed. And so these parameters, this is delta sigma and this is delta epsilon, I'm motivated because these are the parameters where I expect icing model to exist. And then I also want to look at some other point where I expect it to be disallowed. And so I have to compute different blocks corresponding to the differences between delta sigma and delta epsilon in each case. And so you could do that using the scalar block code, which is on Docker. And so you just take the difference between delta sigma and delta epsilon, it happens to be this random number, and then you just run this code. So for delta 1, 2, and delta 3, 4, this is what I was calling delta ij and delta kl. The rest of the parameters are exactly the same as previous lectures, the number of poles, the number of spins, the precision, etc., the number of derivatives. And I have to do this for the different combinations of mixed blocks that occur. And so we have two combinations that occur. So that's why these differ by a sum. And so I just run this code, and then this will fill up my directory. I mean, I already ran this before with various mixed blocks. So this is what all these ZZ bars are. So these are just tables of derivatives in terms of Z and Z bar around the crossing symmetric point for the various specific mixed points I want to look at.
Can you show an example of the format of this output of the block?
Okay, so it's the exact same format as the single correlator format. So it's just a list of polynomials in delta, where delta is written as x. Remember that x is just shifted delta, it's shifted by spin and by d minus 2.
So it computes the derivative of the block.
Yeah, so it's computing derivatives of cross blocks, these f's. It's computing derivatives of cross blocks around z and z bar equals a half as polynomials in delta, which is rewritten in terms of x, and that's exactly what you have here. So these are just huge degree polynomials, and this is the reason why you need so much precision. Because in general, whenever you're dealing with very large degree polynomials, you have to have a huge amount of precision. Because, you know, like this is some approximation, and like, you know, it's going to differ very, very hugely when you change x by even a small amount. And so here we have tables, and so like this is taking no derivatives, this is one derivative in terms of z, two derivatives in terms of z, no derivative in terms of z bar, etc. The format's exactly the same as the single correlator block format.
So for someone who wants to use this, is there a simple way to do a consistency check given this output?
Yeah, so in the lecture notes, I described how to compute the blocks by hand in detail, and I give worked out examples. So you can just compute the blocks by hand, and then just compare it to the output of this code, and you'll see you get the same answer if you were careful about your normalization. This is an exercise I believe Joshua has been doing, and which I encourage all members of the audience to do. But this is something which is worked out in detail.
Something for something easier than without having to do any work. You can just check the consistency. Just to be sure that you're interpreting the output correctly.
Well, I mean, but I don't know anything. Look, there's nothing simpler than just comparing the calculation. I mean, look, you do the calculation very low order, so it's not that hard. I mean, like if you do the calculation just to order r squared, you know, then like that's not something you do in maybe 20 minutes or something, and then you can just check that you get the same numerical result. I mean, I don't really know what other consistency check you do. I mean, because like, you know, of course, this is not just literally the derivatives of the cross blocks, this is also multiplying by the product of poles such that you get a polynomial in delta. Because, you know, originally derivatives of cross blocks are these meromorphic functions of delta. It's only after multiplying by the numerator that you then get this polynomial. But I mean, this is a check which you really have to do. I mean, I unfortunately have done this check hundreds of times. You know, because you always want to make sure you're using the right conventions. Okay, so yeah, so this is what this thing looks like. And so then I can run this wrapper code, which just assembles all these constraints. And so, I mean, you know, just to briefly flash what the wrapper looks like. Again, this is analogous to previous cases. And so you just have a list of constraints. This is for the even sector, this is for the odd sector. And remember, so these are the V's we just discussed. So in the even sector, these are 2 by 2 matrices, which is what we have here. These are these F's with the different labels of sigma and epsilon. I call sigma delta phi here. This is the minus representation. These are now scalar constraints. This is exactly what I wrote on the board before. And then I insert 2 operators and assume that they're only relevant operators. That's what I'm doing here. And then I just assemble these various constraints. Yeah, I'm going through this very quickly because it's extremely similar to what we discussed in previous lectures. Like really, the only novelty is the fact that this is a 2 by 2 matrix instead of being a single matrix. But this is why the notation is always like 2 brackets, because the notation always allows for matrices. And so just in the single correlator case, it's a trivial matrix. Now in this mixed correlator case, I have 2 by 2 matrices, and if you had even more mixed correlators, it'd be a 4 by 4 matrix, etc. It would just be like a bigger matrix for each cross unit constraint. Anyways, so now I can just compute this input. So here I do it for this value of delta sigma and delta epsilon. This is the value I expect to be allowed. I can also do it for this value of delta sigma, delta epsilon. This is a value I expect to be disallowed. Just for fun, I'll do this third value as well. And then, okay. And so then, as usual,
so just to
yes.
make sure, in this polynomial matrix programming setting, there was no parameter you can put into SDPP to choose how you select the sample points of values of x. That was all done automatically, is that correct?
I think that's done automatically. It's possible. Okay, it's possible there might be a way of customizing that. I mean, like in this. So there's kind of like a back end of this wrapper code, and so it's possible that might be part of the back end. Although to be honest, I don't. But it might also just be automatic. There might be just like a standard way of doing it. Anyways, so what we've done is we've computed these inputs, which are these XML files here. And then, just as in the single correlator case, the next step you have to do is you have to transform the XML files into files that STPV can process. So this is called PVM to STP. This is the exact same thing as the single correlator case. So like I won't, something really to say. Sorry, I need to connect to Docker. Not connected to Docker. Yeah. So this works exactly the same as in the single correlator case. Now connected to Docker. This is still starting. Yeah, for some reason Docker uses an extraordinary amount of energy. So when I have Docker running on my computer, like the battery just runs down like in minutes. So this is why I get to do it. Great. So now Docker is running, and it is now computed. It's turned this into the right STP format. I'll do it for this point. I'll do it also for this point. Now that I have it in the right format, I just run STPV for these points. Okay, so for instance, I will run it for this point, which I expect to be allowed. And so just to explain the parameters, again, this is very similar to the single correlator case. So what's going on here? So I'm running Docker. This is just the folder where I'm running it. It's running STPV. I'm using 4 nodes. I'm using this parameter file, which is called params.stpv. It's the same parameter file I used in previous lectures. This is just parameters of like, various cutoffs when you decide you're dual feasible, etc. And then the input file I'm using is the input file I just created. But this is all like basically exactly the same as the single correlator case, which we discussed in the previous lecture. So now STPV is running. And
sorry, it looked like you had more options here than the previous
here?
example. No, like the stuff that's shown down here, the parameters.
Oh no. This is sorry. Is this? This is from a previous run. So like you should only look starting here.
Yeah. No, I understand, but there's a bunch of more parameters
Here?
Yeah, than you previously.
I don't think so. I think it's the same. I mean, like these parameters are just like whether or not you allow like to find primal feasible, find dual feasible, whether or not you allow jumps. There's precision. There's the definition of these thresholds. There's these parameters, which to be honest I don't really understand, and they never really change. There's complementarity, which usually makes a huge number, processors per node, and these other two things.
Actually, what is this max complementarity?
Max complementarity is basically like there's some cases where max complementarity, I guess, is the difference between P objective and dual objective. So there's some cases where the difference becomes huge, and you just want to make sure it doesn't run forever, and so that's why you want to cut it up. Anyway, so this is a point that was supposed to be allowed, and so we find the same pattern that we found in a previous lecture, that when it's an allowed point, P objective kind of grows until it triggers this primal feasible jump, and that basically says they're never going to find a solution, and thus it's an allowed point. I mean, really it's a maybe point, because the way the Bootstrap works is that it rigorously says something is disallowed, or it rigorously just doesn't say anything. Okay, so this is a point that could be allowed, and this is what we expect. Let me also run a point that we expect to be disallowed, so this 147, which we have generated the input for. And so in this case, we expect, again, this will look very similar to what we saw in the previous lecture, that the Bootstrap will just, the P objective will just get smaller and smaller and smaller. It's approaching 0, i.e. it's finding a solution. And so this is what you expect to happen, because this is a disallowed point.
Actually, can you explain the output above this? No, like the below. No, further down. This block grid mapping.
Okay, so I mean, this is basically saying like when it's converting the input into the explicit, matrix that the SDVB is then running on. And so I think this is basically saying the size of these numerical matrices. Because like remember, like the way, as we discussed in the previous lecture, the way SDVB works is that it takes polynomials and it turns them into just big numerical matrices. And so this is basically saying like the size of the numerical matrices in some complicated form. Okay, and so here, so there's going to be some kind of fluctuation, but eventually it will start going down. So you can see that, in the beginning it starts at like 10 to 26, it briefly went up a little bit, but then it starts going down, and then it'll just keep going down forever. And so instead of just watching this thing go down gradually, which is a little boring, I will just jump ahead and show you the results as this thing goes down. We can check back on it in a moment, make sure I'm not cheating. What is this result going to look like? So this is what it's going to look like. And so this is something I actually ran, back in 2019 when I was doing this using Docker. So this is just to prove that you can really do this using Docker. It's a little tedious, but it's not that bad. You can do this in like a day. If you write some code to kind of automatically run Docker like 100 times. So here in this plot, the x-axis is delta sigma, the y-axis is delta epsilon. I basically looked at this grid, which is like these kind of light gray dots. And then the ones that are allowed are the blue dots, the ones that are disallowed are the ones that are light gray. And you see that you in fact get an I. Now, I did this for fairly low number of derivatives, what's called lambda equals 11. And so that's why this island is not that small. Then again, it's not that big either. I mean, you see like the x-axis is going from like 1.405, 1.43. And so that is pretty good. I mean, like it's not as good as Monte Carlo, but like this is just something I did on my computer in a day, 3 years. So this is showing, so this little x is showing the zoomed in plot, which is the thing you see on the right. The plot on the right, I did using higher Nmax. For this, I didn't use Docker. I did it on a cluster because it'd be a little tedious to use Docker. And you can see you already get a very big improvement, where the island shrinks significantly such that it's already almost as small as Monte Carlo. And then, I can show you a video. I can find this.
By the way,
Yeah.
did you scan over OPE in this plot?
Excellent question. In the lambda equals 19 one, I did not scan over the OPE, but I did impose permutation symmetry. Scanning over the OPE would make it even smaller, but that would require even more time.
Okay.
This Docker just uses up a huge amount of memory. I guess it's because I'm using all 4 of my cores to run this thing. Okay, so this thing is going down to 0. It's clearly going to 0. We don't have to do the whole thing. So let's okay, because like I want to show you Bootstrap Island. Okay, that's might be hard to find. This is fun video. Okay, let me just here it is. Okay, so let me play you this video. This basically shows how the island, the dicing model has shrunk. So this was kind of like the original island, and then as they improved scanning over OBs and mixed correlators and everything, increasing Nmax, you see the island gets smaller and smaller.
Can you pause and say just which island is what?
Okay, so this was the original plot they had, I think, from the original Bootstrap icing mixed correlator paper. So this is some like allowed region you get. This is just some crap. Although it's not totally crap. I think this point might be the random bond icing model. This is the regular icing model, which is where you expect it to be, but it's a fairly big island. This island is roughly analogous to the island I showed you in my slides.
So that was mixed correlator.
This was mixed correlators with the gap assumption. These are only 2 relevant operators, but that's it.
And the derivative order is.
I think it was probably lambda equals 19 is my guess. And then the improvements in the subsequent papers is that they first of all imposed permutation and variance, which is kind of for free. They also did OBE scan.
This permutation invariance is a trivial thing, right?
It is. Well, it's a trivial thing
why
conceptually.
Was it imposed initially?
Well, I guess they just didn't think about it. Sometimes people aren't as smart as they should be. And then which is significantly smaller than Monte Carlo.
I'm
Now,
sorry, in the successive improvement, what has changed?
well, I think the first improvement was doing OBE scan and permutation invariance and improving lamp and max. The subsequent improvements, I think, were just going to much higher lambda, much higher group. Now, since then, I think there's even more precise estimates. So this video was made a few years ago.
I guess in probably going to higher derivatives, you also take into you consider much higher polynomial degree for the approximation of the blocks.
Yeah.
So that's what's actually.
Yeah.
right.
So as I said in previous lectures, like the thing you want to improve is the number of derivatives, but the thing you're forced to improve is the number of spins and the amount of precision, because otherwise you just don't get something numerically stable and you just get disallowed everywhere. And that's what slows it down. Because you start having huge degree polynomials, you have like a huge list of constraints because you have like many spins, and that's why this takes a long time. So this is the best result as of a few years ago. Since then they have even more precise, I think it's like 10 digits, but already this is much more precise than Monte Carlo. Okay, so in the few remaining minutes, I can show you a couple tricks.
But is there an expectation of how small it's going to shrink to with this correlator?
I don't think so. I think, yeah, these are all exploratory.
I mean,
Because
this year there are some new results, right?
Well, there was some paper by Ning and David. I don't know if the paper already came out, if it's about to come out, where like they do mixed correlators with more operators. So not just sigma and epsilon, they include like the first irrelevant
But I
operators.
guess my question isn't whether, I mean, I can certainly imagine in practice you can become more, but just as a matter of principle, if you go to operate infinite derivative order, just based on this 3 mixed correlator,
Yeah.
I think some people at least don't expect that to shrink to 0 size.
I think the expectations are not go to 0 size, because I think, you can see from that video that like that's just decreasing nmax, and like the amount of shrinking is not so great. That's not.
But there are many possibilities it could shrink.
I don't have a strong opinion on it. Like.
But there isn't even an order magnitude estimate how much it can be shrink.
I mean, you could do some extrapolation by doing many different values of lambda, and then extrapolating lambda goes to infinity.
But this extrapolation is not always.
Exactly. I'm very skeptical of such extrapolations. So.
I mean, would they shrink by a factor of 2 or by a factor of million in principle?
No. Yes. Okay. So the one other thing I wanted to cover in the remaining minutes is looking at the spectrum. So the idea is that, okay, so we have this small island, and so and we know this probably corresponds to physical theory because the order belongs to Monte Carlo. And so if we look at the boundary of this allowed region, at each point on the boundary we have a solution, an approximate solution to the crossing equation. So we just have literally a crossing equation, and then we have like approximate values for all the OP coefficients and scaling dimensions up to however we truncated it, say up to spin 20 or something like that. And that is an approximate solution to the crossing equation. And so that means you can just look at that approximate solution, and this gives you the CFT data not just of delta sigma, delta epsilon, but of all operators that show up in this OP. So in particular, this would show, like say we truncated spin up to 20, then we would have scaling dimensions and OP coefficients of all operators up to spin 20 in both the even and odd set. And you can ask, well, how good is the spectrum? So like say I looked at the boundary of this island and I look at the spectrum at every single point on the boundary, like how much does it differ and how well does it compare to the expectation? So there was a study done by David Simmons-Duffin a number of years ago, which I'll briefly show you some of the plots. But let's start with something earlier. So previously we discussed how when you minimize CT, it seems that the minimum is kind of corresponding to the Ising model roughly, right? So we have this plot. This is the minimum of CT in terms of delta sigma. This red line is what the Ising model is, and it's approximately like that. So this motivated a study by Slava and David and various other people where they looked at the solution to crossing at the minimum of the Ising model, and they looked at the spectrum, and they got these plots here. So these plots, the x-axis is delta sigma, and the y-axis are various operators in the even sector for spin 0. So the lowest operator is the expected delta epsilon operator, which I guess has dimension 1.5 roughly. And then there's various other higher dimension operators. And so the interesting thing is that where the Ising model is, which is roughly 0.5181, you see this transition in the spectrum. So like there are a different number of operators to the left of the Ising model than there are to the right of the Ising model, where left and right is in terms of this parameter delta sigma. And so this kind of explains why a kink occurs, because the number of operators is changing. So another way of saying that is that a certain OP coefficient is going to 0, because there's some extra like spurious operator, which generically for some reason exists in the spectrum, but the moment you go to the actual physical theory, it disappears. And that's why you get a kink, because it's a discrete change in the spectrum. So this is showing what's going on with the scaling dimension. The plot on the right is showing what's going on with the OP coefficient.
Sorry, the interpretation of, so why would this 2 and 3, do they become one operator in the actual IC model?
Yeah, I guess you could say that. Yeah, because it's kind of the whole thing rearranges. So it's like here there's 5 operators, here there's 4 operators, and so one way of thinking of it is that like the third becomes the fourth becomes the fifth, etc. You know, another way you could say is maybe the second and third combined as one. And then but you can also do it.
Is there a actual rigorous logical foundation to this statement? Because of course the actual theory doesn't exist on the left and on the right.
Yeah, it's a little hard to say because it's like you're talking about theory space. You're talking about basically solutions to crossing. So like the rigorous statement is that you have solutions to crossing, you know, for generic values of delta epsilon, delta epsilon, at least at some finite truncation.
Well, but you want to make a statement that the actual spectrum is approached both from the left and from the right, right?
Yes.
Whereas if you look at the actual value in the middle, like one could also say that maybe you don't have any prediction at all because it's kind of
Because it's a sharp jump. Yeah, so I guess you have to say maybe like the one approaching from a certain direction is the one you prefer. Yeah, I mean that's actually an interesting point. That sometimes there's like a preferred direction, which is where you think the actual physical theory. So the other thing I just want to say is the plot on the right shows the OP coefficient, and you indeed see the like some of these most of the OP coefficients are staying at roughly the same magnitude, but some of them are suddenly becoming much smaller. You know, which I guess has to do with the fact that like one of these extra operators is disappearing. And so this kind of explains why you get a king. And then later, a few years later, there's a paper by Davidson and Stuffin where he looked at the boundary of this island, the one I was showing you before, and he looked at a spectrum around all the points on this island. And then, so this is a plot. So the x-axis is the spin. We're just looking at the even sector. So sigma, epsilon, OP. The y-axis is the twist, dimension minus spin. And the size of these circles is basically how much the spectrum varied as you went around the boundary of the island. Because he used that as kind of a metric for how much you should trust the spectrum. And so the bigger the circle, the less it varies, and the more you can trust it. And so the point is that for the lowest twist operators, pretty much no matter what the spin was, you got a pretty good estimate for what the scaling dimension was. You could also get kind of the second lowest twists, but once you go beyond that, it starts becoming a little fuzzy. And so this is one of the major drawbacks right now for Bootstrap, is that it's hard to accurately get high twist operators from the spectrum. So even for the simplest case of the IC model, you can only get the lowest couple twist operators. Now, how do we even know these second lowest twist operators are correct? Well, in some cases, it's Monte Carlo estimates, and you can compare, and you actually do get a very good comparison. And so we do have good reason to believe that the spectrum, at least for the lowest guys, is pretty accurate. I think Monte Carlo also has issues getting very high twist operators. So, but for the ones we can compare to, it seems to be accurate. Also, what's interesting is that large spin is not the problem, it's large twist. So as you see here, even up to spin equals 40, you know, it's basically whatever your spin cutoff is, as long as like you're looking sufficiently below the cutoff, you can get pretty good estimates. It's really just the twist which seems to be the issue. And so as I'll discuss in next week's lecture, the reason why you wish you could go to higher twist is because that is how you would access, say, like black hole states and like holographic sequences. And so it'd be very interesting to go to higher twist, and that right now is an open problem. So that's something which I think would be great for people to work on. Okay, so I think we're out of time. The only other thing I was going to discuss is like hot starting, but you know that's just some technical detail. Like, I mean, just to say it in a word, so it's like when you're on the Bootstrap, like say I'm doing delta sigma equals 2, previously I did delta sigma equals 1.9, I can use the result of 1.9 to make the value of 2 go quicker. Because like the way the Bootstrap works is that you start with some like initial value of these variables capital Y and lowercase y, which we discussed in the previous lecture. Usually you just start at some random value, but if you know a good value from doing a previous run, which is very similar, then you can start at that good value, and this makes the Bootstrap go quicker.
Sorry, but how is that put into STPP?
So the way it's put into STPP, yes, I don't want to go into details because we're kind of out of time, but like the idea is that, so you have these checkpoint files which are given out by STPP, these .ck files, and so what you do, okay, so I'll just give a couple details, although I won't actually run it. The idea is that you run STPP, and there's an option to use a checkpoint file to initiate it. Here, actually. Here. So this is an example. I'm not going to run this, but like, so here I'm doing a bound on the stress tensor OP coefficient, which is an algorithm I discussed in the previous lecture. I add this extra option, which is initial checkpoint directory, and I use this directory of this checkpoint file for another bound on CT, which had a slightly different value of delta sigma. And so that just makes it go much, much quicker. So like, I I can actually show you an example because I ran these things earlier in the week. And so there was an example to show.
For the checkpoint to work, you need the number of the variables I mentioned so to be all the same. You just like very.
Yeah. So this hot starting, so it's not the most general thing because like you have to have kind of like the same space of stuff. So it's like it usually only works if you're just like shifting something very simple like delta sigma. Okay, so here's an example. So like this is where I ran this stress tensor B coefficient bound using a checkpoint, and so here it only took like 43 steps to finish, whereas like previously it took actually I don't know if I have the well, previously it takes like 100 steps, you know, so it gives like a factor of 2 gain, and the bigger the system it gives much bigger gains. So like, you know, there's some other examples I have somewhere here.
Sorry. Yeah. Can I ask? Are you supposed to put the checkpoint that is the final, the end of the process of minimization for another point, or somewhere in the middle?
I mean probably near the end. I mean look, it's more of an art than a science, right? You know, so like I mean that checkpoint was near the end. You could also just use the final thing if you want. But like, you know, in cases of like finding feasible or dual points, it really drastically improves it. So I have some example here where you see it takes something like 2 steps once you, so here's an example. So like, this is where I was like doing the Z2 single correlator bootstrap. I was looking at this value like 1.5, which is supposed to be disallowed. And I used a checkpoint from 1.6, which is also disallowed. And here it takes 2 steps to finish. So this is much quicker than what it would take otherwise, which is like, I don't know, something like 46 steps. And so this is like a really important thing. So like in practice, you should always do this because especially when you're doing some huge bootstrap, you know, it might be that it would take like a week for the initial value, but then for subsequent values, it only takes an hour. And so that's why it's very important to use hot start. Even though it is more of an art than a science. I mean, like sometimes to get it to work, you have to kind of fiddle with parameters. Okay, so that's basically everything I wanted to cover today.
When you are actually running the Bootstrap, I think your hot start will be improved by the extremal function, right? Extremal functional method.
No, that's a different concept. I mean, extremal functional method is if you have an approximate solution to crossing and then you read off all the safety data. I mean, okay, you could say these are maybe conceptually related because like the idea is that you're using an approximate solution to crossing to then look at a different solution to crossing, which is close by.
Yeah.
So you could say it's conceptually related, but
I mean, is it actually used in the when you are running large scale Bootstrap?
using is the extremal functional method
Yeah.
used? Not as far as I know. There was some paper actually by Paulos where like I think